Show on the road. So where we left off the last time was with tensor data structures. Please note, of course, that there is a chapter, a section at the end of the book, towards the end of the book, Appendix F, that goes into more details on those data structures. And so where we're going to begin today is custom loss functions. And so one of the loss functions that he creates, we're going to get is one called the Hoover function. Before we go into the code, for anyone who's interested in learning a little bit more about the Hoover function, there, if you do a Google search, you'll certainly find a tremendous amount of material. But basically, it's a way where there's the mean absolute error that's used for a loss function and the mean squared error and so on, which work for various numerical regression problems. However, there are certain problem areas around using those all the time. And that's where using Hoover loss function, which combines both the MSE and the MAE, allows the loss function to be easily differentiable, and of course robust to outliers. Those are the problems with the MAE and MSE. And this is useful, especially when you're going to use this loss function for gradient descent. And so this is what the function generally looks like. If you want, there's even a way that if you wanted to convert this to a classification problem and still use this idea of a Hoover loss function, it's possible to do that. So that being said, let's go to the code. He defines, he uses the California housing data set that's built into scikit-learn. Scales standardizes that. And so for that, he plots the Hoover loss function based on his definition for it that you can see on the left. We've done up above. And it follows this exact pattern that you would expect to see. Any questions up to this point? All right, so moving on. The point with this, if you wanted to use, well, the whole point of this is you've defined this Hoover loss function. Let's use that into our model, and where we will set it up where we use the loss function defined as the Hoover function that you've defined above, custom. And sure enough, when you run that, it works, just as you would expect. It works. However, what if, well, the problem is you can save that model, but you can't save the model. The saved model won't recall or won't know what you mean by Hoover function. This is defined externally, external to the model. And so for that, he begins to walk everyone through, well, the ways to do that would be create another definition, or create the Hoover function as a class. And so that's what he does on page 386 to say what it created as a class variable. I'm jumping quite a bit here. Create as a class variable, and then call the function that way, save the function. As long as you're always available, that this class variable is available, you can run your model, save your model, open up that model, and still get it to work. Any questions up to this point? All right. So we could spend a little bit of time, as he does, with some of these class definitions. For instance, this Hoover class, and the reason why he codes it this way he spends this page, page 386 in the book. This is the part around saving and loading models that contain custom components. He spent some time to explain that you could create just a simple basic configure the loss function this way. There was a key point here. I wish I had highlighted it. The threshold will not be saved. This means that you'll always have to specify this threshold value and the Hoover function every time when you save a model and before you call and rerun that saved model. And so this is the more appropriate way that he says to be able to functionalize or modularize your code so that as long as this class variable is available, your save model will function correctly. So is there an interest to walk through this construction of this class function?
Sure.
Sure. Yeah.
Very good. So Wenchang, if you could help me a bit here, because this is a little beyond my skills. But as he says, when you set up this class, the first thing, of course, the parent constructor will input in this arbitrary value for the threshold, be used as a parameter, and you set that when you define the function, and then of course you define what this how a Hoover function is set up, which is these 3 lines over here, and it gives you back the 3 different loss functions that you need output.
Yep.
Right.
Right. Yep. And I think I mean for people who are not as familiar with subclassing is it's basically using your you write a class, then you're basically inheriting from whatever you pass in. In this case, it's chars.losses.loss, right? And we basically inherit from the class that's called chars.losses.loss. And if you look into that, Mash, if you don't mind, kind of Google this class.
Sure. Or I can also, just like we used to do before, I can give you control if you want to create.
Sure.
Go ahead, take over.
Yeah. Well, I guess we can just quickly Google.
Just go ahead.
It's basically subclassing from this, and now you can call different methods from this class, and let's see what's in there. And I think it was saying it can handle standard hyperparameters like name of the loss and reduction algorithm, something like that. And again, I think chars.losses.loss is pretty much similar to tf.chars.losses.loss. Keras and TensorFlow, Keras and tf.keras are pretty much merged after 2.3, I believe. And yeah, so and these are the parameters, right? Name that was mentioned here, and also the reduction algorithm, which is right here. So you can actually, perhaps instantiate a method that passes into the parent class. So, and that's what he meant here, by having this, quarks, you can
The
actually,
argument. Those are keyword arguments, right?
exactly, you can actually pass in, uh, you can pass in arguments back to the parent constructor. So, and the way how you initiate the parent class is by having a uh, super parenthesis dot init. So then you're initializing all the um, instance methods and instance variables. You're basically initializing the parent class, keras.loss. And there's a lot of discussion that could go into what super does and how you can use it. And one of the ways is you can actually just by calling super here, uh, which is super.config, right? So by calling super, you're basically calling keras.losses.loss parenthesis dot config get config. So even though you didn't define get config, but this was inherited from keras.losses.loss. So that's a kind of a brief explanation of how subclassing a, a, a Keras class can work. So yeah.
So it looks like what you're doing is you're defining this new Huber loss, and it inherits from the TensorFlow.keras.loss losses.loss. So it knows that it's a loss function, and the call method in there is, I guess that's defining what the new loss function should be. And what it returns is the actual loss function.
Exactly.
And then this get config is supposed to return a dictionary with the hyperparameters, and that's this asterisk asterisk base config. So you're getting this base config, which is a dictionary, and so you're returning it as a new dictionary with the threshold parameter added. Um, so so it looks like that's what it's doing.
The threshold parameter is part of keras.losses.loss.
No, it wasn't. That's the whole point. You added a new parameter by means of this loss function. You defined this new threshold parameter and added it. And so now when you when you instantiate an object with this Huber loss class, it's going to know that it's a loss function, but it's also going to have that parameter inside it, that threshold parameter that's been added to its parameter dictionary. That's what happens on the last line. You're adding the asterisk asterisk base config is the dictionary of parameters that are associated with this loss function, but you're adding this new parameter called threshold, as you can see, which is going to be assigned the value of self.threshold. The new key is the new keyword of threshold, and it's going to be assigned the value of self.threshold, which is that 1.0 that you gave it in the top.
Yeah, Mash. Thank you, Joseph. If you can give me the
You
remote
got it.
control one more time.
Mhm.
So look at this call, right? So what this does is your new Huber loss call will replace the call here. Um, and your new get config will replace this, but but it's calling the supers get config instead of directly doing this. It will return the base config and plus the threshold. So you're overriding the parent classes get config and call methods. So you're overriding them, and that's in a way you're customizing your own loss function, but inheriting some of the functionalities from your parent class. Okay.
So normally the get config would return the dictionary of parameters from the loss function, But with this new, as you said, as Wenchang said, the new, when you execute this get config, you're replacing the old get config, which returns that dictionary, with this get config, which basically returns the old dictionary plus uh, a new keyword value pair, which it's adding. The new keyword value pair is threshold, and so the keyword is threshold, and the value is self.threshold.
That's right.
It's
Okay, back
because
to
of
you,
this
Mike.
super call. Base config equals super
Mhm.
config, super's config, and super being set up here to then take this call.
Right. Okay.
Hmm. Out of curiosity, has anyone had to build custom class functions? And usually, what was the use case for doing so?
I had one experience.
Mhm.
So, so this was I was using Allen NLP. So
Mhm.
that's built on base of PyTorch.
Okay.
So we were implementing adversarial loss. So that's why we had to write a customized function,
Sure.
and we're more or less referring to one paper
Mhm.
where it was use case was basically semi-supervised learning problem. So we had been given large number of unlabeled data, unstructured text, and then
Mhm.
there's a very few labeled samples. So by the use of adversarial loss, we were able to um, basically what's that word? Form the embedding by adding some kind of noise, replicate what we do in Vision, but not very specifically, but on the similar lines. So that's why custom loss was imperative to write in that matter, and it actually follows the same pattern like in TensorFlow and PyTorch. Like you have one initial init function, and then you have the main body function where you actually define the loss.
Yep.
um, and also sometimes you also have like if your loss, if you are updating the weights like manually like you do in PyTorch,
Mhm.
then you will have to have one callback method for that as well.
Got it. Which is what's distinctively different with PyTorch. And because you had built it around that specific custom adversarial loss uh, use case, I'm sure it worked. It did exactly what it was meant to do.
Yeah, and generally as written by Geron, that whenever you want to have your hyperparameters updated or customized in some form, since
Mhm.
it's not savable in normal form, just like function, that's why we can leverage the parent or like loss function or metrics or regularizer in that matter.
Basically, a way to not write everything from scratch. If you can inherit from somewhere else, then usually,
Yeah,
PyTorch or TensorFlow's own classes, basic classes, you can save a lot of work, and that's how a lot of classes from Fast AI are built. They're just inheriting from PyTorch and building your
yeah,
own, functionalities.
true.
Very good. Well,
Now, the only fly in the ointment here is that this fancy method of creating this custom class, it doesn't actually work. If you try the notebook, at least on my machine, it failed when you tried to load the notebook. Whereas the simple method where you just pass it a function, you pass it a loss function with a threshold of 2, that did work. In other words, the method where you just define a function called create Hoover, that worked when you saved the model and then loaded it back. But this new Hoover loss class, when you save it, it works fine. But then when you load it, it doesn't.
Well, let's try it. If we set this Hoover loss, I just redid it with a threshold of 2. Now we're calling it, well, I should have seen this. We're still calling it with a override with a threshold of 2 here. And it, well, converges up at least in 2 epochs. But
Yeah, but we haven't saved it and tried to read it again yet. See, he's got this line grayed out because it doesn't work. He's got it commented out because it doesn't work.
because he's doing, yeah.
So, if you try that, which I did, you uncomment that and try it, it will fail.
Yeah, that's a smart way of telling check the PR.
Did you try it?
Yeah.
Oh, because on my machine it fails. That's weird.
Yeah, and I wish I knew, because there are some where
interesting.
I know. There's a cell further below.
Yeah, it works on my as well. Yeah.
Now, FYI, I updated everything, so I'm on Python 3.86 or something, and took the latest TensorFlow and so on and so forth. Updated all of my packages just late this afternoon, early evening. All right, let's keep moving on. So now that we've done, we've worked with Hoover class, we could, of course, define all sorts of other custom activation functions and other classes. If this is, bottom line, if you can create a loss like this, why not just do the same thing, follow that same approach for creating custom activation functions, initializers, regularizers, constraints, and so on, which he gives an example of doing over here. Clear session, go ahead and set this up, and once you have it, we can create, for instance, this glorot initializer. We discussed this, I think, about 2 or 3 chapters back. You can create your own regularizers or so on if you don't like L2 or L1. You have a certain preference, as I don't know if Steven's on. However way you want to do it, you could use that as your custom regularizer and set it up to run, and it'll work. Now, here again, he uses the loss function for default MSE. The metric that he wants to apply is an MAE, and that will certainly run. You can save the model and call it again and whatnot. But then you call it again and pass through the different custom objects, these activation functions, initializers, and so on. The custom ones, that too also works. He goes into this other part. Wencheng, if I can get your help again with this one, he turns that regularizer into another class, again, using that subclassing effect over here. Almost to me, it looks the same. I'm afraid I tried to explain it to myself and I couldn't follow. So the self-factory.
It's the same as before. It's just creating a new regularizer object that has that scale factor in it already. So you can see that the call function is returning the regularizer is returning the L1 thing, the absolute value of the weights, the sum of the absolute value of the weights, but multiplied by this scale factor, which you give it as an input, and then it returns that as a dictionary, the scale factor and its value.
And its value. Interesting. And so that dictionary, that regularizer, here's the part that, okay, so why it confused me was he then goes on to call it next, but as if it were a function with with a default this value, which should be the factor that's fed in here. Um, this part just how can you set up this class like this, but then call it again as your regularizer, like so, with a value 0.01.
I think that's what that dunder call does. It allows you to use
Double
this class as a you can use it as if it were a function and give it your input. So it doesn't have a fixed input. It can have whatever input you give it.
Oh.
So that
And would require
0.01, pardon?
It would require an input. I apologize for interrupting.
No, that 0.01 that you're providing as an input, that becomes the scale factor that it's going to use.
Yeah, the under call is a way to call a class and make it operate, like Joseph said, like a function, as opposed to the without dunder call that we used in the loss is just an abstract method defined in the base loss, which means that any subclass of the loss will have to define call in it in order for the function to work. In this case, the dunder call is what Joseph said. It acts as if my L1 regularizer is a function to which you can pass the parameter.
Right. That's what dunder methods do.
And he says in the book, he says on page 388, or if you have the Kindle, it's right above the custom metrics section. He says that you must implement the call method for losses, layers, and models, or the dunder call method for regularizers, initializers, and constraints. So you have to have those type of objects have to have a call method.
Mm-hmm.
Yeah, the call method, as we saw in losses, if you go back, I was looking at it. If you go back to the code, you'll see that it's defined as an abstract method within the base class.
Yeah.
And when you define an abstract method in a base class, that means any subclass must have a definition for the abstract method, because you're basically taking an abstract method and making it kind of concrete. So you must have an implementation of an abstract method defined in a base class in a subclass.
And he says specifically that the dunder call method must be in a regularizers, initializers, and constraints have to have that dunder call method implemented. Mm-hmm. So that's what we're seeing there.
Yep.
And
now it makes sense.
Mm-hmm. Yeah, that probably makes sense, because that just means these ones are have to be called and need to be called. So they need to have a dunder call methods. So
just to add, this is a life cycle of this regularizer class, in which certain how do I say it? There is a certain way of calling a sequence of methods, and whatever uh, class that we define, base class, or sorry, the subclass of the parent class, and we try to override the method. So in that how do I say it, the parents class sequence of those calls, those subclasses method will be overloaded, and they will be called instead, because we are using the instance of the subclass here as opposed to the parent class.
Mm-hmm.
Yep, I'm nodding.
and you can see like my L1 regularizer is not actually inheriting anything. It's just overriding, and but it's still subclassing from the parent class. So so it's just overriding, but it's not using anything from the parent class. Yeah.
Interesting. So I guess he does that just to make this point. Doesn't seem necessarily quite practical, but that's the general idea. So he saves the model, and then of course he's able to load the model again, that same save model in again, be able to define for that its different regularizers and weights initializers and so on. However, he does this section did seem different to me. So this custom objects list, it's got the curly brackets, but how he seems to use this to define something.
It's the same
Yeah,
thing.
it looks like he may want to be defining those things. That's like a dictionary of custom objects, so that when you retrieve after you save the model, or no, you are loading the model that's saved, and
You're loading the saved model.
right, and you're telling it which objects you need to get out of it, I guess.
Well, if that's the case, then would we, if we were to call any of these items, like if we were to call my regularizer, for instance, is that the output that we would get?
You probably want to do model dot my.
And then do I have to put a this after it?
I'm not sure. I didn't like that. No object, no attribute.
Sequential object might not have that.
Yeah, I think so. In the layers section, if you go down, there they are using the kernel regularizer, the constraints, and the initializer as a source of those custom objects. When they have tried to define the sequential Keras model in the dense layers. Uh, it's just two cells down the custom objects module.
Over here?
I have a separate here. Please go back to where they have defined the custom uh, objects.
Sure. Bear with me one moment. Is you set the model, but if we're the object,
Yeah, in the dictionary form, the key value form, and when they are trying to define the custom layers, they have used that there. So I'm not sure. It's on. Let me.
you're welcome to either take over my screen if you want.
It's on because I can see it on my. Yep. I would
Is it
request
in the
remote
book?
control. Just yeah. Let's custom layers. Just that.
I'm sure
Because
there's. there's a method you could call just like do dir model, and there's probably a method you can call to retrieve these custom objects.
Yeah, and there are in the subsection of other custom functions. So that was the section I was looking at because I am using PyCharm. Uh, so
You're using PyCharm to run the notebooks?
yeah,
You're
Other
brave.
custom functions is farther up then.
okay.
I think.
The custom functions.
Other custom functions. Custom metrics. Hoover metric. Stream metrics. Oh, 3.
These are the custom metrics, and these are the custom objects. So here,
Yeah.
and just here only with respect to the custom loss functions. If you can just search this here, I think so. My L1 regularizer, you will find a custom layer in which they have used this.
Got it. That's up over here.
Yeah. I know this is the definition of it, but in the sequential model, this is the stuff that I was trying to. Yeah. So how and why have they used this my L1 regularizer in that sense with respect to the custom objects, because they are passing in those layers, and I think so internally they might try to refer when it's trying to load the model here, because the model is saved and serialized on the disk. So if they're trying to deserialize it, yeah, here in 234, if I try annotation, yeah, here. So here they have saved it to the disk, okay, and if they're trying to load here, that is serialized from the disk. So these are the custom objects that they need. So that's the that helps in serialization and to map those custom objects to the objects that we have defined. If I'm not wrong.
So when you save the model, it knows those names. It knows that my underscore L1 underscore regularizer, my underscore positive underscore weights. It knows those objects are in it, so that then when you retrieve it, you can actually get those objects back out.
Or more like you've defined those objects, you have them in memory here. When
Yeah.
you call the save model, you have to specify when the save model requires my M1 regularizer, refer to its definition in my memory.
Yeah. So that's the mapping that we're trying to map it back. So that's why they have used it here. Thanks.
So kernel in that panel that's labeled 230, right? It's that one, and that's in green, that has a green box around it. So this activation, these and the layers.dense in the second layers.dense, he's got an activation, a kernel regularizer, a kernel constraint, a kernel initializer. It almost seems like these things are known, that it expects that a dense layer can have these things. In other words, a dense layer knows what an activation is, knows what a kernel regularizer is, knows what a kernel constraint is. It just seems like that is built into it.
He must have defined it up above. Maybe I went too fast, but he must have defined that up above so that it's not like that's the typical definition of a dense layer.
Well, the dense layer is a built-in function from TensorFlow, and I'm just thinking that or a built-in class. And I'm just thinking that that class must know what a kernel regularizer is and an activation function and so on. It's those things are pre-specified so that if you tell it one of them, it knows what you're talking about.
Yes, Joseph. I think that they are predefined in the dense class, and so that's why you can specify those values for like the activation can be relu. We saw that even in the two classes back when, or two chapters back when we were defining the deep and wide, he had different activations and stuff like that. So yes, activation, regularizer, constraint, initializer are all part of the dense definition.
I wish there was a simpler way to code this. The idea behind defining and constructing a neural network seems intuitively easy enough. It's this Pythonic way of coding it makes it a little harder. And I'm speaking strictly for myself, from my perspective.
In what sense?
In the sense, in the way that it's being defined here, for instance, just laying it out this way, it doesn't seem quite as standard as someone just mentioned a little while ago, how in a couple of chapters ago, we defined it in one way, but this is a little bit more different. Sort of, there's more custom definitions here.
Yeah.
Well, I mean, one question that arises is why is the order the way it is? When you presume that these things are to be done in serial order, the activation followed by the kernel regularizer, followed by the kernel constraint, and so on. Why is it in that order?
Not really, Joseph. It's just keywords, so you can specify them in any order you wish.
Yeah, I was going to say the same thing. Yeah, you
It's
can
just
any
keyword
order.
arguments, so the order doesn't matter.
Right.
They're not positional arguments.
Mm-hmm.
Yeah, and notice when you load the model, that my L1 regularizer no longer needs that 0.01. So when you write that class and specify it, specify 0.01 when you train it, and you no longer have to. I think it memorizes the threshold or whatever parameter that you specified when you train it. And that was mentioned in the text later on. So yeah, just to keep that in mind.
Right. Wenchen, do you want to continue on with custom metrics in the interest of time?
I think we had a good I think it's 11:15. Yeah, let's continue a little bit, I guess, then we'll call it a stop at 11:30 sharp. And yeah, so and so I think we probably wouldn't be able to finish my sections. That's probably yeah. Okay, so let me take over the screen.
Sure.
Second. Okay, can everyone see my screen?
Yep.
Okay, let's go to the custom metrics. I think we're following, generally the same ideas instead of, loss functions or activation functions or regularizers. We're just customizing metrics now. And I think it's important to keep in mind that I believe, let me just see, I came across one thing. It was this post. And I had a question on this. I think Karas made a statement as of September 17, 2019. I think it's important to kind of know what the difference is between tf.keras and Keras itself, because we've been switching around. I think we were using tf.keras, and now we're all using Keras itself. But I think it's important to kind of know this. Keras 2.3.0 is the first release of multi-backend Keras that supports TensorFlow 2.0. And this is as of September 17, 2019, from the Keras team. It maintains compatibility with TensorFlow 1.14, 1.13, as well as Theano and CNTK. This release brings the API in sync with the tf.keras API as of TensorFlow 2.0. So it means Keras from this day and onwards, this is now in sync with the tf.keras API. However, it does not support most TensorFlow 2.0 features, in particular eager execution. So maybe Keras has a later version, or maybe we installed a later version, I'm not sure. But if you need these features, use tf.keras. This is also the last major release of multi-backend Keras. So it's the first release and also the last major release. Going forward, we recommend that users consider switching their Keras code to tf.keras.
Doesn't Geron always use tf.keras rather than well? No, not really.
Not really, he doesn't. That's what Wencheng said. And so once again, another example of Google taking over an open source community.
Yeah. So I think at the very beginning, I think he imported Keras from TensorFlow. So I don't know how that's different from how this Keras is different from tf.keras. And obviously we're calling tf.keras from tf. But just to keep in mind, we should always try to use tf.keras.
I think it's the same engine. Since you're importing Keras from TensorFlow, it should be the same as tf.keras.
You're very, you're not audible quite as well. Do you mind repeating?
Yeah. Did my voice get cut off?
Just to add, nowadays we are all switching to tf.keras because all the upgrades and hooks that are there to the TensorFlow are all here in the TensorFlow library. So we as I do not know about the community, but I specifically use tf.keras everywhere because it gives me the peace of mind that all the API changes and the feature requests that are upcoming are actually there in the API that I use. So that's my 2 cents.
Yeah, and it says development will focus on tf.keras going forward. So I don't know what that is, why they make the changes. But it seems like they're just merging everything with tf.keras, and they will do focus on this going forward. So I think it's probably good to see what's going on here. Let's just this is tf.keras. Let's see what tf.keras.
I think that every time you see Keras in there, in Geron's code, it means tf.keras because he says from TensorFlow import Keras. So every time you use Keras, you're referring to that Keras that's been imported from TensorFlow.
It could be.
So the bottom line is I don't think we have to worry about that. I think we're within the tf.keras universe and we're not using the old keras anymore.
Okay. Okay. You may be right. Okay. So let's
Yep.
keep on. Yep. All right. So back to custom metrics. Okay. So we should clear our session as always before we build a new model. And this is just basically using two sequential layer, one layer with 30 hidden units, activation using Selu, Lacan normalization, input shape equals to input shape, and the last dense layer has one neuron. And using the MSE, mean square error, NADM as optimizer, and metrics create Hoover 2.0. So let's run this. So in here he used this loss and metrics as the same thing. And he was saying basically they're very close and they should be the same, but they're not the same. But it's generally just due to floating point precision errors, even though the mathematical equations are equivalent. Okay. Now, this is a very interesting topic, streaming metrics. He was saying basically, if you're, if this is one batch and this is one batch, and you shouldn't calculate just based on each batch independently. You should actually take the total positive, in this case, I guess, true positive divided by all positive, which is the precision metric, instead of, calculating independently each by each. So therefore you need something that's called streaming metrics, meaning it can record as it goes. And if we use keras.metrics.precision, it will be able to kind of record that. And as you can see here, I think, yes, the results is 0.5 instead of 0.4 after taking the second batch. Then he goes on to creating an entire class for streaming metrics. This is also very interesting. Basically, he's inheriting from the keras.metrics.metric and super or initialize the parent class and self.threshold equals to thresholds, and defining a bunch of other instance methods. And notice now this dot add weight, where does it come from? It comes from this keras.metrics.metrics. And only by super this, then you can inherit this class method in passing some arguments. And if you want to verify that, then you go to keras.metrics.metrics. Let's see right here. Right here. So that's the add weights method that we are inheriting from. Name, shape, aggregation. Believe. Let's see if I can. Nope. Initializer. Right here. Okay. So, and that should be the name parameter. So then we define our custom metric function, Hoover FN. Again, it's similar calculation as we saw before. And this is the state update function. So metric equals to self.Hoover_fn, and so it's calling this function Hoover_fn and passing it y_true, y_predict, and to get the metric. So we're not necessarily, directly calling this function, but we're just using it here. And then we call the self.total dot assign ads. So this assign ad comes from this add weight methods, and then you can further call this assign add method and pass in the tf.reduce sum and tf.size of that. In the end, then you get the results, self.total divided by self.count. That's basically averaging the Hoover loss, or the mean of the Hoover loss. And again, this is similar to what we've seen before, calling the parent class get configuration, unpack that, and pass that into a dictionary, and with one additional metric, one additional dictionary item threshold. So let's run that. And we instantiated with 2.0 as the thresholds. Okay. And the variables. I think the variables is probably the parent classes methods. Set states, clear session, building a model again with 2 layers, 2 dense layers, specifying the loss as create Hoover, metrics as Hoover metric, optimizer, NATM. I got a little confused on why he wants to keep using loss exactly the same as metrics. Anyone has any ideas why he does that?
I think he wanted to make the point that you could take that Hoover function, you could use it both as a loss, you could use it as a metric, that this idea that you can customize quite flexibly.
Mm-hmm. Okay, got it. Okay, so you could also do it this way. I guess it's a little simpler. And now you're initializing with name equals to name and d types equals to d types. And look at what's happening now. Now you're taking off the Quark's dictionary argument and doing it in a simpler way. And also, when you inherit class, it's always good to check the flow of the classes. If you're dealing with multiple inheritance, which normally you should avoid. But if you're doing sequential inheritance, it's also good to check which class gets executed first. So it's good to, I think, yeah, it's good to check that. um, just so you know when you're writing complex OOP Python code. Okay, so let's keep going with this new class. Everything else is pretty much the same. And yeah, I mean, that's pretty much it. Everything else, he's just changing the way how you write, you know, the Hoover metric class. And so I think it's probably a
Yep.
good point to stop.
I had a query.
Yep.
Why have they used the mean here with respect to if I think so with the Hubermetrics, they are trying to use a mean to yeah here. This is the sample weighted mean. What does this signify? Let me this
Simple.
yeah.
Oh, I think it has to do with how you want to, what your samples weighting is. Let me just take a quick Google search. And, fix.
I think that it's specifically telling it that it wants the output to be the mean of the to be that it automatically knows that instead of having to define the result as the self.total over self.count like it did in the previous definition, now it's going to know how to do that implicitly without having to implement that, because it's a special kind of a metric called a mean. It's inheriting from the mean, so it knows what the output is. He's basically just simplifying the function that he wrote the first Huber metric, the first Huber metric under streaming metrics that he wrote. He's just defining that to inherit from the general metric class, but the second time he's telling it to inherit from the mean class. So somehow that means he doesn't have to say that the result should be the mean of the individual uh, uh, elements, that it knows that that's what it wants for the output. And then the other thing he did is instead of defining the Huber function inside, he used the previously defined function which he calls create Huber. Remember he defined that before. And so the new class is simplified. It's somehow much simpler looking than the older class, because he's eliminated the Huber function as one of the methods. He's eliminated the result, and what else? He still has update state, get config, and the init part. But yeah, and
So
from the init, he also gets to eliminate the self.total and self.count. He doesn't have to keep track of that anymore, because that's what the mean will do.
cool. So if we visualize this on a TensorFlow graph or something, or tensor board, we will see with the epochs the convergence to a central point that's easily identifiable, uh, in the sense, because this is a metric that is being used to converge. So if I look at here, the first Huber metric was zero point 0.8 in the first epoch, and the second epoch has a 0.2631. So in that sense, how can we intuitively uh, uh, so you get my point. How can we intuitively understand it? Yeah, I get that. We can use that as a mean, which this mean is used as a method that simplifies this metric from a visualization perspective, because or a convergence perspective. I'm just trying to understand that.
Yeah, I'm still thinking about it.
Okay. Anyone else has any comments, questions before we wrap it up? We will continue with custom layers next session.
I guess another interesting thing is to look at the definition, to look at the Hoover function the way he has it first, the way he first defines it. And you notice that the squared error has a factor, has an extra scale factor of 1/2, and the linear error has an extra offset of 0.5. And if you go back to where he graphs the Hoover loss at the very beginning, here, let's see, it's right under custom loss function. Yeah, that's it, right where he graphs that. So I was wondering why, he defined it that way. So I thought, well, long story short, the reason why he has to put that extra scale factor and that extra constant offset is in order to make the functions match at the boundary, which is at 1. It has to match at the threshold, not only the function, but the derivative of the function. And that's the reason why you have the offset and the scale factor that he has. Where he says z equals, he says z squared over 2. That's the L2 part of the metric, and the L1 part of the metric is I guess it's z minus it's the error minus 0.5, or is it plus or minus 0.5? I forget how he's got it.
Minus 0.5.
Minus 0.5, yeah. So the point is that the reason for this scale factor of 1/2 for the squared loss and the offset of minus 0.5 for the linear loss is in order that the derivative and the function will match at the threshold. And you can try it by putting, say, take away those scale factors, just leave it to be squared loss equals TF dot square error without the factor of 2, without being divided by 2, and set linear loss just to take off that 0.5 offset. And when you run it, you'll see that it looks funny. And you'll see that the slope doesn't match at the, you can try it, whoever's running the notebook there, just try taking off the scale factor and the offset and see what happens. Go one cell up. Just go one cell up, yeah. In Hoover function, in Hoover FN, in that block, yeah. Wipe out the factor of the divide by 2 and wipe out the minus 0.05. Yeah, and then wipe out the 0.05, and then run that cell. And then yeah. See what happens at the plot. The slope doesn't match. The function itself is continuous at the boundary, but the slope doesn't match. So that's why you had to have those. That's why he has a special scale factor and the special offset in order to make the not only the function has to match, but you want the slope to match too, so it's smooth.
Cool, thanks.
But then the weird thing is that later on, when he has an arbitrary threshold, he changes the function again. He changes what the Hoover function definition is again, and it's more complicated than dividing by 2 and subtracting 1/2. There's some function of the threshold. It's farther down, I guess, where he redefines the Hoover loss function when you have an arbitrary threshold. Yeah, right there. So see now, the squared loss is the same as before, but now the linear loss is a function of the threshold. And I believe, I haven't verified this for myself, but I believe that the reason for that is the same in order to make the function and its slope continuous across the threshold. Anyway, just thought I'd throw that out.
Where do we usually use Hoover loss?
I guess you want the benefits of L1 loss, which is robust against outliers, plus the benefits of L2 loss, which I'm not sure. Yeah, I'm not sure why you'd want the L2 loss.
Yep, I recently came across an article from Jonathan Hui. He used it in the Q-learning, reinforcement learning. That's the one of the algorithms for that, and he used the Hoover loss there to converge uh, that I'll to a point. So
Mhm.
uh, maybe I will share a link in the Slack.
That'd be great. Just put it in the Slack. Yeah.
Yeah.
Also, the description that I used at the beginning of our session was from another book. It's a course from Berkeley, and there's the last paragraph. Attempting to take the derivative of the Hoover loss function is tedious and does not result in an elegant result like the mean square error and the mean absolute error. Instead, we can use computational method called gradient descent to find a minimizing value of theta. So again, theta being that threshold that you're trying to use the Hoover function to try to minimize. Yeah, I'm sure there's specific cases like in Q-learning to use Hoover functions, but I think this is just a teaching pedagogical alternative to try to, instead of using just direct gradient descent.
Yep.
So what this does is if it's small error, it returns this, and if it's not, returns this. Is that what it is?
Yeah. If on the right, on the outside of the threshold, it gives you L1 loss, and on the inside of the threshold, you see those two. If you're looking at the plot, where it has the red, yeah, up above, yeah. Okay. So outside the threshold, meaning to the left of the left red bar and to the right of the right red bar, that's outside of the threshold. It's using a straight linear loss, L1 loss, and inside it's using the L2 loss, which is the mean squared error.
So it's this plus this.
Yeah. In other words, instead of the parabola, that's what you'd get if you used mean squared loss. It's modifying that, and in such a way that the outliers don't, that it's more robust against the outliers. The outliers don't blow up as fast.
Got it. So it's using this within the -1 and 1, and outside of that, it uses the linear.
Yeah, the linear. That's right. The mean absolute. Yeah.
Got it. Okay. Okay. So the loss is basically smaller outside of that.
Yeah, outliers don't cause such a huge loss as
Okay.
it would with a mean squared error. Yeah.
Got it. Okay. Cool. All right. Well, that's it. Thank you, everyone. Really great discussion. I know it could be challenging, especially for people who haven't dealt with much of inheritance and subclassing, but it is definitely important when it comes to customizing models and being able to kind of tweak your own models. And this is one of the most, I think, valuable skills for data scientists. Uh, Otherwise, everyone can call, tf.Harris, and because it's just easy and intuitive. But being able to customize your own models, makes you irreplaceable. So, okay. Anyone else wants to say something before we wrap it up?
I was just going to say that if you feel like we need an extra session to cover this chapter, that's fine. I'd rather cover it, I'd rather cover it well than just rush through it.
Yes, please.
Absolutely.
So,
Absolutely.
yeah.
Yeah. yeah, I mean, we do have 2 more sessions, so we'll play by the ears, see how it goes. And I will probably gauge interest, to see if we want to add a session or add some time at least covering PyTorch version on this. Because I think it will be helpful to kind of look at both sides of the world rather than just TensorFlow. So,
Yeah.
okay. On that note, I want to thank everyone for joining and thank Mash as well for co-hosting the session with me. Really appreciate it. Everyone.